Assalamualaikum warahmatullahi wabarakatuh. So here we are with topic 21, the last topic, titled as Alternating Current Circuits and EM Wave. However, we are only gonna cover up to 21.6 only, where the subtopic are resistor, capacitor, inductor separately are connected to AC circuit. Then what happened with these three elements, we're going to connect them together. Three ni comes together, put into a series circuit. Put them into series. Next, we're going to study the response of the power and close the topic with the concept of resonance. Right? So let's start with 21.1, resistor in AC circuit. So what about it? First and foremost, we need to start with the general concept. One of it is this one. What is this? This is an expression, an equation representing sinusoidal curve. What sinusoidal curve? When we talk about AC circuit, then we can't run away with the shape of the sinusoidal shape, right? Sinusoidal. So this particular shape, this particular curve, this particular graph curve is equivalent to this general expression that you have learned in physics 1. So what is this? This is the instantaneous voltage. Maknanya at that very specific time that you put into, let's say you put 5 seconds, okay, 5 seconds, or you put 10 seconds. So at that specific time, what is the voltage? That is what you meant by instantaneous voltage. What else? The V maximum represent from the graph, for instance, the maximum value produced. Okay. So the highest peak. And the rest over here, we would say that 2 pi ft, f is frequency, all right? And bear in mind, mathematical skill you had to ensure that the product of 2 pi ft had to be in a bracket, then only you put into the calculator as sign product, yeah? So overall, we can as well write the 2 pi ft as omega. So that's going to be equation as omega t, representing 2 pi ft. Right, so what is omega? Recall that is angular frequency. Angular frequency. Alright, so the study is when we connect a resistor into a series AC circuit, we find the current and voltage are in step. Okay, are in step. So in step means they are in phase. So likewise over here, when the voltage increases, the current also shows an increment. So they are in sync with one another. So due that it's in sync, we can consider that again they are called as in phase. In phase. And let's say that we are interested in terms of how differ they are in term angle, then we can say the angle itself is 0, right? 0. Now you have to remember the shape of the graph. You will find that the voltage itself as the orange shapes. Okay, I'm going to cut this away. Okay, I'm not going to start. I am only, okay, we are going to make things simplified by only sketching one cycle. So what does a cycle gonna looks like? This one. Okay, so hold on. I'm going to straight move on to a capacitor graph. Now observe, this is a scenario or the response of the current when capacitor alone, pure capacitor is now inserted into AC circuit. So once again, draw it similarly. So goes up and then goes down. Now how about again another one, the last one, inductor, it goes off the same one. So the shape of the voltage graph is of the same one. Right. So however, the response of having a resistor inside an AC circuit, you're going to see it should in phase. Maknanya shape sama. Yeah? But it's also correct to have if you have something like this. So what makes them different? So this, the one that I just sketched just now, is a situation where the value of the R is larger as make comparison with the one given or sketched by the book. So that's what make it different in terms of how high or how low the shape of the I maximum. It depends on the value of the R. But what we are looking at is at the shape. Okay, so it mimics the same shape as the V voltage just now. And from here, okay, from here kita can look at the next one, which capacitor. This is a case whereby kita akan buat laju lah sikit. You're gonna see that a capacitor, the shape for a cycle, okay, look again, a cycle, so it stopped over here, is a resemblance of a cup, all right, an open cup, an upright cup, right? So hopefully you get the idea of how to sketch. And where else for an inductor, for again a cycle, you're gonna see a big cup, however in inverted version. Now let's get back. So that's the idea of how you're going to sketch how I curve, I graph gonna look like individually for R, individually for inductor and also capacitor. Next, right? Next. We're going to see that the concept, I'm going to skip first the concept of how I derive I current. You're going to see here the value of the I itself keep changing. So you notice here is 0, here is 0, but somehow over here is maximum, and of course in between is of some other value. Maknanya I dia berubah. So due to that, okay, when we treat in terms of the calculation, right, it's as well important to note there is an average value of current, which we call it as RMS current, RMS current. So to get this RMS current is actually half average, but yet with a square root. Okay, and therefore this expression is as well valid if, let's say, you are talking about VRMS, voltage RMS, which an average value as well, which is gonna be V maximum, and to be divided with 2, which is half, but with a square root. All right, so hopefully you see the correlation. Now, yeah, we have another here, okay? So VRMS, so you can see the correlation is quite easy. So long that you have V maximum to be divided with half and a square root, then you are arriving with the average, okay? RMS, we call it root mean square, RMS. Right, once again. Now, so these are the notation used in this topic. So this is current, which resembles the instantaneous at that instant, at that time, at that specific time. Is it at 0 second? Is it at 5 seconds? So this is the symbol. Okay. While the voltage gonna be with delta small v. If you're interested with maximum value, then delta v. But you have noticed bahwa in calculation in class as well, it's as well acceptable to simply write it as such. No, nothing wrong with it. Okay, nothing wrong with it. Acceptable of the same thing. Now, therefore, when we rewrite again the concept of Ohm's law, which VIR, so you just had to be concerned about how we put that notations here. If it's RMS, then RMS, okay? And again, if here is V maximum, oh yeah, we have this one. So maximum, then I would respond as the maximum product as well. So that's gonna cap the idea of how we correlate maximum and IRMS. Okay, once again, what is IRMS just now? IRMS represent a value of average, representing in the case of current, so average currents. Okay, how do we get it? Just divide it by 2 and together with a square root. So how do we arrive the correlation over here? To be done in the class itself. Alright, now let's have a look at this question. So this question basically interested to find RMS current. So what do we have over here? We have an AC voltage source where the source itself is alternatingly curved there. Output there going to be with this expression. So it tells you that 200 just now is the V maximum. This is what it meant by this expression. So it's connected to 100 ohms. So we have R over here. The question is asking what will be RMS voltage. So what did you do? The V maximum to be divided with 200 divided by 2 with a square root. That's going to get you the answer. So the RMS current, there are two methods. Either you start off with now that you have VRMS, you proceed with Ohm's law, VIR, and use the RMS product for the replacement substitution of VRMS itself. So here goes. But it's also be correct if you kind of proceed with again Ohm's law, a little bit panjang lah sikit Ohm's law, but this time you put it as maximum. So in conclusion, by that expression, by that technique, you're going to arrive with I maximum. Now that you have the I maximum, yes, proceed with dividing it with 2/2 and square root. That's it. So of the same technique. Alright, so I like you to try and attempt exercise 21.1. And here goes. I help you out with the equation of power. So earlier, recall that power is IV or I squared R. But then again, because the terms is average power, let's make it a little bit different, whereby you had to consider all the products to be the RMS product, right? Try. Alright, now let's have a look at the capacitor. So earlier just now, we have looked at the response on how to sketch the graph itself. Alright, so the keywords here is that why is it that the voltage when it is 0, however the current reaches the maximum. Alright, so these are sort of the answer lah. You're going to see that in a sense, when current is at the maximum value, the voltage tends to be 0 because a capacitor has an ability to store charges. The moment that it's being charged up fully, you would have noticed to the left and to the right of the plates are filled up with charges. And since it's filled up, means that it's unable or doesn't allow charges to transfer to the other plates. Dia tak bagi dah transfer. Kalau tak transfer, means that current is cut off during that time. And therefore, we will say that when V maximum occurred in a capacitor, then during that time, current would turn out to be 0. Okay, let's find this explanation in the text itself. Right, it says here, when time is 0, when time is 0, there are still no charge on the capacitor, and is the reason why current can flow effortlessly, tanpa gangguan. Dia tak ada halangan untuk current tu lalu. However, again go back to the graph. When the maximum voltage occurred over here, the current would turn out to be 0. So you need to remember the concept lah. So V maximum 0, I kosong. I maximum, V kosong. So they are vice versa of one another because of the behavior, the capacitor itself. Alright. So now, this one. Okay, we're going to explain this. So based on this expression, based on this particular graph, look at the time equivalent to 0. You have noticed that the current has a value, in fact, maximum value. And therefore, we would say that the current leads the current I leads the voltage. Okay, why? Because at that time 0, the current has a value whereby voltage is 0. So that's why kita kata I leads the current. However, kalau kita nak rephrase dalam bentuk berbeza, rephrase semula turns out to be the voltage is now lambat, lags the current. That's the idea. Now, how come the angle comes in? So earlier just now when it is a resistor, dia punya sudut dia is angle dia 0. Now where does this come from? Now let's go back to the graph. Now having a graph of a cycle which stop over here, we are going to find that a cycle is also composed of 360, and therefore we can say is that the shape over here, or what's missing probably, or perhaps you find if you want to mimic of the same shape as the voltage had to be added with this. So how much is this? This is a quarter of a cycle. Again, how does a cycle of 360 looks like? So that a quarter is actually resembling the shapes as such. So this particular shape is 1/4 of a cycle. And how much is a cycle? It's 360. So divide 360 with 4, you arrive with 90 degree. So that's how you get the 90 degree. Now here, right, we are going to treat once again Ohm's law, but a little bit different. You find that rather than writing it as just C, but C is a capacitor. It's not a resistant. So we have to reintroduce again Ohm's law. So what does it say? We put it as X, XC, meant for capacitor. Now, let's fast forward for inductor. You find mimic of the same expression. We are replacing R with X. So, the question, what is X? X is reactance. Reactance. It's similar to the resistor in one way, but belongs or due to the existence of a capacitor or an inductor. So what are the value of XC? Right, once again, reactance. Let's find the terms in the book itself. Reactance, it's not over here. Here goes, reactance. So we call it for capacitor, capacitive reactance. And you find it was inversely proportional with omega capacitor. 2 pi f can as well be written as omega. So that's why such this. So turns out to be omega C. Now, let's make a comparison with inductor. We find Ohm's law as it is. Ohm's law, VIX. So in terms of the names, what it does, bring the names. X is again reactive because we are talking about inductor becomes inductive. Sifat, inductive is sifat lah. And bear in mind the whole thing here gonna arrive with a units of ohms, including XC earlier. Right. So let's now first attempt the question example on regards to a pure capacitor. Means that only a capacitor, one single capacitor is substituted or inserted into an AC circuit. Now this example shows that you have a capacitor CC connected to a terminal of AC generator where having RMS voltage 120, and at that time the frequency is 60 Hz. So now you are going to see for a capacitor it's really affected by the frequency, whereas the resistor, no, resistor as it is. So the question, get the reactance. So what is reactance earlier for a capacitor? 1/2 pi FC. So here goes. So let's double check. And they are also asking for RMS current. So simply substitutes the expression 2 pi F and also the value of C given earlier. Now the next moment is asking for RMS current. So proceed with Ohm's law. It's just that now R is being replaced with inductive capacitive reactance, sorry, capacitive reactance. So notice that it carries a units of ohms over here. Okay, ohms over here. So arrive with RMS. That's it. As simple as that. All right, give a try on the given example, the following example, 21.2. All right, let's look at the last one, inductor when it is inserted into an AC circuit. So earlier, we have mentioned that in terms of sketching, we're going to look at the shapes equivalent as if there is a cup being inverted. So our concern is, why is it that it behaves as such? Number one. Number two is, we're going again the concept of leads and lags. Yeah. So let's start with lead and lags. So notice that when time is zero, what happened to the voltage? Voltage is zero. However, I is of a value and yet is a negative value. Therefore, in this manner, we say that voltage has larger value, and due to that, voltage leads the current. Voltage leads the current. And finally, the particular shape of inverter cup, right? If we are to mimic together similar, so we have to add another 1/4 to it. So that's the reason again 90 degree. Okay. So it says here, voltage reaches maximum value 90 degree before the current. So that makes the voltage lagi laju, leads the current by 90 degree. Alright, so what sort of question gonna comes out or tested for you? Very simple. In a case where pure inductive, quite similar to the previous one, they give you the inductor L value, unit Henry, and voltage, for example, 150, and again of the same frequency. So by asking what is the value of inductive reactance, simply put the expression in 2 pi FL. Right, and arrive again with units ohm. And finally, getting the RMS current, apply Ohm's law. Again, case closed. Right, as simple as that. All right, do attempt this exercise. Right. Okay, we're going to stop here for the first part.